Okay, here's another lesson video for further mathematicians. We're looking at exercise 7a. We previously looked at some inverse trig functions, and today we're going to look at the differentiation of those inverse trig functions. And I suppose it's linked to these graphs. I wonder if you can remember which graph that is. Either way, we'll come on to that in a bit. First of all, we're going to look at what happens when you differentiate. Now, this is really just a revision of the chain rule. And it says we're going to differentiate this sine of x plus 2, and you might recall that sine, cos, minus sine. Minus cos is the easy way to remember this. So when if we're going to differentiate, I'll leave a gap, I think the answers appear there. So I think this becomes cos, because sine becomes cos, of the x plus 2. But then by the chain rule, what we're meant to do is differentiate the x plus 2. But as it happens, that's 1. So if times anything by that, I think that's the answer. Let's just, yeah, the answers come up perfectly. So this second one, it says, interestingly, t equals something in y, so that's why we've got dt by dy. Other than that, it says 7 cos of 2y. Now, cos becomes minus sine. So this becomes 7 times by minus sine of the 2y. And then I have to times by the differentiation of that 2y, which of course is 2. I reckon that's minus 14 sine of 2y. The third one is, it starts off at minus sine, so minus sine and then becomes minus cos. So this becomes minus cos of the bracket. But then I times by differentiation of the bracket, which is minus 3 when I do that. So I reckon I get 3 cos of 5 minus 3x. And the last one, well, it's minus cos, and minus cos, it says at the top, becomes sine. So this is going to be sine of 2x minus pi by 2. A bit weird, but there you go. And then I times the differentiation of that, which is 2, so I reckon it's that. So there you go, a bit of a reminder. Now, we talked about these graphs just now. Can you remember which one's which? Just to put your mind at rest, then let's go through them. The first one is the inverse cos. So the one that comes down has a negative gradient all the way down there. So this has got a negative gradient, I think, all the way through it, is the inverse cos graph. Now the second one is probably this one up here. This one is the inverse sine graph. You'll notice this has got a positive gradient. And this one is also positive. And what's this? Well, it's obviously the inverse tan graph. So they are worth knowing, and I want you to draw them into your notes and make sure you've got a picture of them. Notice this one goes up to pi by 2 and down to minus pi by 2, but doesn't. That's kind of like asymptotes, top and bottom. Whereas these, their asymptotes don't really apply here, but they do, you'll notice, go and stop dead at these points. They don't carry on, these stop dead at these points. So just make sure you know those. Alright, so some proofs. These are standard rules that you're meant to know. This is the rule that you're meant to know, and it's to say if you differentiate inverse tan of x, you get 1 over 1 plus x squared. And you might think, why on earth is that? It's true. Well, I'm just going to run through the proof. So proof number one, part of the proof that you have to do initially is say to yourself, well, this can move over, and if I rewrite that, I get that x is the tan of y. Notice the inverse tan becomes a tan when I move over. So x is tan y, first step. Second step is to remember that if I differentiate the tan, I get sec squared. Now, look, if you're forgetting things like this, if I differentiate tan x, I get sec squared x. Now, luckily, some of these are given to you in the formula book, but it would help a lot if you remember that. So this says tan y, so that's why the answer is sec squared y. Now, remember also we had an identity, and the identity started with cos squared plus sine squared equals 1. There should be some x's in there and stuff, but you get the idea. And if we divide all of that by cos squared, you get 1 plus tan squared equals sec squared. Now, bear that in mind, it says sec squared, so I've rewritten it as 1 plus tan squared. Why does that help? Because I know what tan is. Tan y is x. So this, by definition, must be 1 plus x squared. And hang on a bit, is that the proof? Well, it's not quite actually. Oh, I see, I've jumped ahead a step. So this really, the reason why this is slightly, looks slightly weird, that says dx by dy. So dx by dy effectively is 1 over. Notice dx by dy, is 1 plus tan squared, which is x squared. And my next step is to say, well, I can flip this over and I get dy by dx. So that's what this proof is doing. So that for 1 over the 1 plus x squared. And that's this proof, which is what they wanted at the start, all the way up here. So this is worth learning, knowing. Okay, there is, well, that's just rewritten it. The second one then is very similar. It says y equals inverse sine. So first step, chuck the sine onto the other side. You get x equals sine y. What's the second step? Well, differentiate it. But notice, because it says x equals, same as last time, you'll get dx by dy. Dx by dy, and of course sine becomes cos. No problem. Now, we know a formula. Our formula says cos squared plus sine squared equals 1. Well, I've got cos, so cos squared equals 1 minus sine squared. Or said differently, cos is the square root of 1 minus sine squared. Now, before I do that, notice I'm just flipping upside down again. It said dx by dy. I want dy by dx. So cos becomes 1 over cos. And hang on a bit, I know what cos is. It's this. And of course sine, we said that right at the start, was x. So rather than writing the square root of 1 minus sine squared for cos, I just write 1 minus x squared. So you could easily have put in a little line in between here which said 1 over the square root of 1 minus sine squared y. And sine is y is x, so sine squared must be x squared. And that's where that comes from. You'll notice then. Now this theoretically could have been plus or minus because I'm square rooting. But I know this graph, the sine is going to be a positive. So effectively I ignore the minus and say it must be a positive. I know what it is. And obviously the inverse sine then is written when I differentiate it like that. That's what we must know. The domain, by the way, is what I was talking about. It stops there and it stops there. This is only valid between 1 and minus 1. The last one that we need to know is the inverse cos. And you'll have seen already the shape of this in terms of what the proof looks like. I'm expecting the cos to move over. Oh, it hasn't got it this time. We better do it ourselves. X equals cos y. Now differentiate dx by dy. Well, you should remember sine cos minus sine minus cos. Cos becomes minus sine. So this is minus the sine of y. But again, I know that cos squared plus sine squared equals 1. So therefore sine squared equals 1 minus cos squared. And therefore, well, I suppose I should throw some y's in here. And therefore sine y is the square root of 1 minus cos squared y. But remember what cos y is? It's x. So I can write sine y is the square root of 1 minus x squared. So the other thing I'll do is, before I even jump to that, I'll flip it upside down a bit like they did before. Dx by dy is that, so dy by dx is minus 1 over it. But I know what sine y is now. So dy by dx is minus 1 over the square root of 1 minus x squared. So yeah, so if we just show you this, don't forget that this is again a restricted domain. The graph only goes from minus 1 to 1. And therefore the differentiation only works between those two values. But again, we've proven this. We've shown that this is true, which is what the derived thing means at the top. Let's now put these rules into action with a few examples. Differentiate y equals the inverse tan of 2x. So, well, we already know that if we differentiate inverse tan, of course, we get this. So the big question is, what happens if it says 2x? So dy by dx is equal to, well, the obvious thing is to write 1 over the 2x squared. But then we have to times it by the 2, I suppose, because it's a chain rule again. So what's that give me? That's 2 over 1 plus 4x squared. And there's the answer. So it's this bit here which I suppose would be easy to miss. Putting 2x into there because it says 2x is kind of expected, but I suppose it'd be easy to forget the chain rule. Second example, now it's inverse sine this time, it's differentiating. So we know we've got this thing going on, 1 over this, so dy by the x is crying out to write 1 over the square root of, well, normally of course it's inverse sine of x, but now it's the inverse sine of that, so it's 1 minus x squared. And then I've got to times it by the differential of this, which looks to me to be minus 1. So I've got a bit of work to do on the bottom, but it's definitely minus 1 over something, and it's the square root of, well, this is of course 1 minus 2x plus x squared, but it's minus all of that. So 1 minus 1 disappears, minus and minus gives me 2x minus x squared. Let's see what the answer says. Yeah, exactly the same, apart from then this answer then looks at it and says I can take out x as a common factor, and then I get x, 2 minus x. So yeah, I agree with that. A couple of questions here. Differentiate inverse tan of 4x. So again, if I was doing this, I'd write dy by the x equals, and I want to write 1 over 1 plus 4x squared. Seems perfectly reasonable, but times it by 4 because that's a differential of 4x. So what's that gives me? It gives me 4 over 1 plus 16x squared. Alright, so this next one, just be a little bit careful. It's the square root of x minus 3. I nearly missed that. I thought it was a bracket. So if I'm going to differentiate this, the obvious thing to do is to want to, it says inverse cos, so it's minus 1 over the square root of, and what am I putting here? It's 1 minus, well, it's the square root of x minus 3 squared. So presumably those two things cancel out. It's not finished yet, by the way, but I'll just tidy that bottom bit up. And that's 1 minus, well, I think it's 1 minus x minus 3. The reason why I say it's not finished is because now I have to times by the differential of the bracket. And what does the differential of the bracket give me? Well, really this is like x minus 3, because this is really what I've done. It's the square root of x minus 3, so it's x minus 3 to the half. If I was to differentiate that, I reckon it'd be a half x minus 3 to the minus a half times by the differential of the bracket, which is 1, so it's that. Well, I don't like the minus a half bit, so it's 1 half of 1 over the square root of x minus 3. And you can see that they can be joined together to give me 1 over 2 root x minus 3. So I'm meant to times by that here. So this is meant to be times by 1 over 2 root x minus 3 times by 1 over 2 root x minus 3. It doesn't look very nice, to be honest. And what's this tidy up to here? This gives me minus 1 over the square root 1 minus and minus 3. It sounds like to me 4 minus x. And I'm then times by this, which I can put the 2 at the front and then do the x minus 3 in brackets. You'll notice I've just joined those two things together. Let's see what the answer says. Oh, good. I'm pleased. That was the one I was most unsure about, that one there. So you've got some questions to do. It's from exercise 7a, page 154 if you're using the textbook. Otherwise, it's in on the sheet. You're basically expected to know these three formulas and use these three formulas. Make sure you do use them. And don't forget the chain rule. We've seen it come up loads and loads and loads, and you're meant to use it when you get a slightly weirder one. So best of luck on that, and good luck.